So oxidation reduction, redox, it's kind of called both of them. So what we're going to look at today is we're going to look at the definition, because there's different ways that you can define oxidation reduction. We're going to look at how do you figure out the oxidation state or the oxidation number of an atom that's in an ion or in a compound. And this also relates to why we have those Roman numerals for the transition metals, because that Roman numeral represents their oxidation number. And then we're going to talk about the terms oxidizing and reducing agents, what those mean. There is a specific way that you balance redox equations. It's kind of a multi-step process that you have to go through. We can actually use what are called half reactions or half equations for these, because we will have the oxidation half equation and then the reduction half equation. And when you put them together, you get the full reaction. But if you separate them into the half reactions, then you can identify like what's being oxidized, what's being reduced, and what's the oxidizing agent and what's the reducing agent and that kind of stuff. And then this all relates to some other stuff that we've learned about in the past, like the activity series of metals, ranks them according to how easily they go under reactions. And then there's a specific thing that kind of ties into environmental here towards the end, where we're going to use something called the Winkler method that involves using a redox titration, or not a redox titration, but involves using redox information to measure what we call biochemical oxygen demand, or BOD, as like to measure like how polluted a water sample is. Okay. All right. So that's all in 9.1. 9.2 gets into what we call electrochemical cells, which basically are batteries. So we're going to talk about like basically how do they make batteries, because batteries, you take a chemical reaction, you take chemical energy and you convert it into electrical energy in order to power something. That's all it's doing. And so we talk about because there's an oxidation and a reduction reaction happening there. So you can talk about the half reactions, and you can talk about the flow of the electricity and how that all works and all that kind of stuff. Okay, so 9.1. Our basic definition, oxidation is, you can define it in terms of loss or gain of electrons, which we call like electron transfer, loss or gain of oxygen, loss or gain of hydrogen. Most of the time it's going to be the first one, okay? And so there's a little mnemonic device to remember. It's called oil rig. So oxidation is the loss of electrons. So OIL, oxidation is loss. And reduction is the gain of electrons. That's the rig, RIG. Okay. When you look at it, single replacement reactions are all redox reactions. Synthesis and decomposition reactions are all redox reactions. And combustion reactions are all redox. The only ones that aren't redox are double replacement, because double replacement, there's no electron transfer, there's ions kind of moving around. Okay. But most of our chemical reactions are going to be redox, those different categories that we've talked about before. So this one is a single replacement reaction. So what's actually happening here is that I'm taking a piece of zinc metal, I'm putting it into, a beaker or some container that has a solution, an aqueous solution of copper sulfate. So it's a solution floating around in the beaker or whatever container. And what's going to happen is zinc is actually more reactive than copper on the activity series. So zinc will replace the copper, and you'll end up with zinc sulfate that's dissolved in the solution, and you'll see solid copper form. So you'll see solid little like reddish brown flecks start to form in the solution. How this relates to redox is we can actually break it down, because really the sulfate ions are not doing anything here. What's really happening is I have solid zinc, and then anything that's an aqueous solution, in the solution, the ions are dissolved and they're separate. So I have copper ions and I have sulfate ions. Anything that's ever labeled aqueous, you can break it apart like that. And so what happens is that's the reactant side. And then the product side, I can do the same thing. But on the product side, I have the zinc is now paired up with the sulfate. So the zinc is now, it's in the ionic form because it's in the compound. And sulfate is still the same. But now the copper is that solid element. So what happens here is, if you notice, the sulfate didn't change. It's sulfate dissolved aqueous, it's sulfate dissolved aqueous. So those are called spectator ions. They cancel out. And then what I'm left with is my redox reaction. So what I'm left with is solid zinc, the element, plus some aqueous copper ions that were dissolved. They're going to react and they're going to transfer electrons. Okay. The zinc is going to lose. The copper ion is going to gain, because what I end up with is now I have zinc ions that are dissolved. They're aqueous, plus now I have solid copper, the element, on the product side. So what's happening here is zinc went from being neutral, having a charge of 0, to +2. That means that zinc lost 2 electrons. So that means that zinc was oxidized, because we just got done saying up here that oxidation is the loss of electrons. So whichever thing loses electrons from reactant to product side, that's what's oxidized. The copper has been reduced. That copper 2+ ion now became just the element copper over here. So it gained 2 electrons from the zinc. And so the copper ion was reduced. So that's the basic premise, what's going on here. And then once I know like which one is oxidized and which one is reduced, I can actually write them in these half equations like you see here, where I have, okay, solid zinc, and I made solid copper, or not solid, I'm sorry, aqueous copper ions in solution, and it gained, here's the 2 electrons that it gained, because they're on the product side. It gained 2 electrons, or I'm sorry, it lost 2 electrons, and those are the electrons it gave away. Copper ion gained 2 electrons, so they're added here on the reactant side, and on the product side, it becomes the solid copper element. So those are, when you hear the term half reaction or half equation, it's what I have boxed in pinks. One of them is the oxidation. So like the zinc one, that would be the oxidation half reaction, because we said zinc was oxidized. And then the copper one would be the reduction half reaction. Okay. That's the main definition. There are other ones. Like I said, you could talk about loss or gain of oxygen or hydrogen, but mostly we're going to be focusing on the electron definition. Okay. But just know that, like for this example, I have iron oxide, carbon monoxide, and I'm producing solid iron, the element, and carbon dioxide gas. So Fe2O3 has been reduced because it started out with oxygen, and now over here, the iron doesn't have any more oxygen. The carbon monoxide has been oxidized because it started with 1, and now over here it's carbon dioxide. Okay. Hydrogen, if you, this is an alcohol right here. So this is something we're going to get to in organic chemistry, but this is an alcohol. This is ethanol, and it can be oxidized. And so notice that it's lost a hydrogen over here. It's lost some hydrogen. And then this is a compound called ethene, C2H4, and it's been reduced. Okay, they added hydrogen to it, and it was reduced, and now it has become this new compound. So we'll see these reactions kind of pop back up when we talk about the organic chemistry stuff next week and the week after. Okay. All right, so oxidation states, you can calculate them. It's really easy. Okay. One thing I want to point out, and I talked about this during first year chemistry a lot because I harp on it because I know that they do this in IB, is that oxidation numbers are written like this with the plus or minus sign before the number. If you write the plus or minus sign after, that's not the oxidation state, that is a charge. Okay. And sometimes, as we're going to see going through this, the charge and oxidation state, they're not the same number. Okay. So here's the rules. Elements have an oxidation state of 0. So if you just have an element, and that includes all of these diatomic elements, okay, all your diatomics, if it's just the regular elemental form and its naturally occurring form, it's 0. Okay. If you have oxygen in a compound, it is most likely going to be -2. There is one exception if it's in a peroxide. So for example, carbon dioxide, oxygen's -2. Water, oxygen's -2. However, this one, H2O2, that's hydrogen peroxide, because that O2 is one of those polyatomic ions. And so in this one, the oxygen's only -1. So you have to be careful for if there's a peroxide, but the majority of the time, oxygen will be -2. If you have hydrogen in a compound, It's always going to be +1, except if it's paired up with a metal. So hydrogen, as long as it's paired up with another non-metal, it'll be +1. When you pair it up with a metal, like sodium, the hydrogen takes the negative charge rather than the metal, because metals will never be negative. Okay. Group 1 and 2 elements, so the alkali metals and alkaline earth metals, they're good. Oxidation state matches their charge, okay, based on that the group of column number they're in. Fluorine is a halogen. Fluorine is always -1, so that matches the charge for that column of halogens. Okay, the rest of the halogens don't always follow that though. Okay. In metals, the charge on the ion is the same as the oxidation state. For example, if I have Cu2+, that means that the oxidation state of that copper ion is +2. Okay, I don't know why it says copier. That's a typo. Should say copper. If you have an ionic compound, the oxidation state of each species is the same as the charge. Okay, so for example, NaCl, if I know that it's +1 and -1 for the charges, those are the oxidation states, +1, -1. For covalent compounds, this is where it's a little trickier. It says, assume that the more electronegative atom has the negative oxidation state, the less electronegative atom has the positive. So in something like CCl4, chlorine is going to have the higher electronegativity because it's a halogen. It's more to the right of the periodic table. So chlorine will have negative and carbon will be positive. And so in this case, chlorines are -1 and there's 4 of them. That means the carbon has to be +4. If you have a compound that is neutral, that does not have a charge, all the oxidation states have to add up to 0. So all the pluses and minuses have to balance out and be 0. Okay. So for example, CH4, the hydrogens will be +1. The carbon in this one's a -1, or sorry, -4, because that adds up to 0 since there's 4 carbons here. Okay. Same thing, NH3, each hydrogen is +1, so that's +3. That means the nitrogen has to be -3 in order for the whole thing to equal 0. If you have a polyatomic ion, the sum of the oxidation states have to equal the charge on the ion. So for example, the sulfate ion, whatever I get, it has to equal -2. Okay. So this is where you have to do a little bit of math. So if I want to figure out, well, what's the oxidation state of this sulfur? Okay. Well, I know that the whole thing has to equal -2. And I know there are 4 oxygens, and I know oxygen from up above is pretty much always -2 unless it's a peroxide. So 4 times -2 plus whatever my sulfur is has to equal -2. So then I just like solve for the sulfur. So -2 equals -8 plus sulfur. Oops, not another 8. That should be an S. So if I add 8 to both sides, this becomes a +6 and the 8 goes away. So sulfur is a +6 in this one. Okay. So there's a little table here that kind of summarizes the rules, and you apply these rules in order from like 1 through 9. So like 1 is supersedes everything else. Okay. So 1, free elements are 0, including the diatomics. Number 2, the sum of all of them in a compound has to equal the net charge. So either 0 if it's neutral or the charge if it's a polyatomic ion. Alkali metals, group 1, they're always +1. Fluorine, always -1. Alkaline earth metals and zinc, always +2. Hydrogen is always +1, except if it's paired with a metal, then it'll be -1. Oxygen's always -2, except in a peroxide, it'll be -1. Halogens are typically assigned -1 unless you have to calculate something that makes them not be -1. So that, because that's a pretty low rule. And then the charge on the metal ion is the same as its oxidation state. There, for example, if you have zinc 2+, the oxidation state would be +2. So you have some practice on here with deducing oxidation states. So some of them are ions, some of them are atoms, some of them are whole compounds, polyatomic ions. And then in section 5, it actually has the names of the ionic compounds where they have transition metals, and it wants you to deduce the oxidation state of the metal ion. That should be pretty easy because guess what? It's the Roman numeral. It's just you put the plus sign in front of the number instead of the number in front of the plus sign like you would do for the charge. Okay. That's where it talks about oxidation states can be represented by the Roman numeral. So for example, Copper Roman numeral 1 oxide, that would be copper plus 1 because the oxidation state would be plus 1. Copper Roman numeral 2, the charge is 2 plus, so the oxidation state would be plus 2, etc., etc. All right, and then balancing redox equations in acidic solutions. So this is typically, there's a way to do it in basic solutions as well, but we pretty much focus on acidic or neutral. So there's a specific method you have to do this, okay? Because right now you have to balance not only all of the different elements, but you have to balance the charges, like the number of electrons as well, because that's all what redox is about, is transferring electrons. So everything has to be the same, all the numbers of the elements and the electrons, okay? Well, right now, if you look, there's one iron on each side, there's one manganese on each side, but look, this side, there's 4 oxygen. There's no oxygen over here. Where did the oxygen go? Okay, so that's a problem. Number one is that there's 4 oxygen on one side, but there's no oxygen on the other side. The other problem is the charges probably don't add up either. If you look, I have a positive 2 and a negative 1. So that's positive 1 on the reactant side. On this side, I have a positive 3 and a positive 2. That's positive 5. That doesn't add up to positive 1. Okay, so we have to balance for all the elements and the charges, the number of electrons. So what you do in order to fix the oxygens is first balance for any other elements. Well, we already checked, okay, and we don't need to balance the iron or the manganese, so they're fine. After you check for all the other elements, then you want to balance for oxygen. And you do it by adding water molecules to the side that has less oxygen. So what that would look like for this one, and I'm going to write skip for this one because they're already balanced, the irons and the manganese. All right, but for step 2, what that would look like is I would have Fe2 plus MnO4 minus, and I'm going to make Fe3 plus Mn2 plus, now I got to add water, but I haven't added enough waters so that I get the same number of oxygens as the other side. So how many waters do y'all think that we need to add?
4.
Yep, we got to add 4 water molecules because the 4 oxygens will match this 4 that's over here. Okay. So once you balance the oxygen by adding water to whichever side you need more oxygen, then the next step is now you got to balance the hydrogen, because when you added water, that also added some hydrogen ions.
Good afternoon. Just a reminder, please return your...
So then I want to balance out the hydrogen, because since I added water, that added oxygen to fix that, but it also added hydrogen. So hydrogen we're going to have to add to the reactant side though. So how many hydrogen ions do you think we're going to add?
8.
Yep, we're going to add 8. So I'm going to stick them here at the beginning. So 8 hydrogen ions. Plus we still got the iron 2 plus, the permanganate ion, and then over here we got the iron 3 plus, we have the manganese 2 plus, and we have our 4 waters. Okay. The last step, so now all the elements are balanced. The last step is we have to balance the charge by adding electrons to whatever side to make the charge the same on both sides of the arrow. So this is where I'm going to have to look at all my pluses and minuses and total up each side. So if I look at this side, so there's 8 hydrogen ions, so that's plus 8. Then I have plus 2 here, that's plus 10. And I have a negative 1. So total on the reactant side is plus 9. Okay. The product side, I have a plus 3 and a plus 2. Water is neutral, so there's no charge there. So I only have plus 5 on the product side. So remember, you're balancing the charge by adding electrons, and electrons have a negative charge. So you're always going to add the electrons to the side that's more positive, because the adding electrons is going to lower the overall charge. So in this one, we would add them to the reactant side because it's plus 9, and we want it to go down to be plus 5. So we're going to need to add 4 electrons to the reactant side. So when all is said and done, I'm going to have 4 electrons plus 8 hydrogen ions, and I'm going to add the state symbols back in now. I wasn't writing them because I was trying to write quickly, but you do need to make sure you include, like, you know, the aqueous and liquid, gas, solid, all that stuff. Plus our iron 2 plus, which is aqueous, plus my permanganate ion, which is also aqueous. And then I'm going to run out of room, so I'm going to have to kind of write mine partially below. But then on the product side, we have Fe3 plus aqueous, plus we have the manganese 2 plus, that's aqueous. And then we have 4 water molecules, and water will always be a liquid. Okay. So now that one that I have written in orange, if I check both sides, all the element, there's the same number of irons, the same number of manganese, the same number of oxygen, the same number of hydrogen. And if I check the charges, everything's going to be +5. There's going to be a same charge on each side. So it's kind of a tedious process, but once you practice it, it's not that hard. Balance all the other elements, then balance oxygen by adding water, then balance hydrogen on the other side by adding hydrogen ions, and then check the charges of both sides and add electrons to the side that's got the higher charge to make it match the other one. So there's a couple here for you to practice with, okay? When you're on your own doing stuff later. All right, last thing that I think we're gonna have time for today is just this definition of oxidizing and reducing agents. So we talked about the terms oxidation and reduction. Well, if something is oxidized, then that is the reducing agent, okay? So for example, and this is going back to the similar reaction to that first one. So I have magnesium and I have a copper sulfate solution. Magnesium is higher on the activity series than copper, so it's going to replace it. So I end up with magnesium sulfate and copper. If I get rid of the sulfate, because the sulfate is going to be a spectator ion, this is my actual like redox equation right here. I have solid magnesium, the element, plus copper 2 plus ions that are aqueous in solution. And I'm producing aqueous magnesium ions that are 2 plus charge and element copper, okay? So then I can identify their oxidation states. So if you notice, they're labeled underneath. So the elements are both 0 because they're just natural elements. And then both of these are metal ions. So since they have charges, their oxidation state matches the charge. We just put the plus sign in the front. So magnesium started at 0 and it ended at +2. So magnesium was oxidized. Therefore, magnesium is the reducing agent because it allowed the copper to be reduced by giving its electrons to it, okay? The copper 2 plus ion started as +2, it ends at 0, so that was reduced. Therefore, it is the oxidizing agent. So some people have trouble remembering these because it's like they go with the opposite. But if you think about the magnesium was oxidized and therefore it allowed the copper to be reduced, so it's the reducing agent. The copper ion was reduced, so therefore it allowed the magnesium to be oxidized, so it's the oxidizing agent. And so basically, if you're given a redox reaction like this, you're going to have to identify what are the oxidizing reducing agents. And so you'll do just kind of like that example where you need to identify what are the oxidation states of all the species. So therefore, you can identify what was oxidized and what was reduced. And whatever was oxidized, that's the reducing agent. Whatever was reduced, that is the oxidizing agent. Actually, I think we can finish a little bit more. Okay, so activity series. We learn about this kind of briefly in 10th grade chemistry, so this shouldn't be totally new. But we're relating it specifically to redox right now. So we typically have all of our metals on here. The metals towards the bottom are less reactive, so like gold is the least reactive. All the way to the top where we have lithium is the most reactive. And so how this kind of relates to some of the things we've talked about today is the most active. So lithium is the highest, more readily oxidized. So they are stronger reducing agents. So things up here like lithium, cesium, rubidium, potassium, they're very easily oxidized. Okay, they react very easily. So they are strong reducing agents. The ones at the bottom, they are less readily oxidized. All these things at the bottom, like silver, platinum, gold, they don't react very easily, so they don't oxidize easily. Therefore, they are weak reducing agents. Okay. A metal at the top can reduce the ions of a metal lower. So again, going back to our example, we always get rid of the negative ion here. Magnesium is way up here. Copper is, where is it at? It's down here somewhere, down towards the bottom. Here's copper. So the metal magnesium is able to reduce those copper ions because it's higher up on that activity series. And so that's why that reaction, that redox reaction takes place, because magnesium is a stronger reducing agent. So it will reduce those copper ions because it's higher on that activity series. So this relates to those single replacement or single displacement reactions. So this is just kind of giving you a visual aid. And we did things like this in 10th grade where you have like a metal. So this is actually, here's the piece of zinc. Here's my copper sulfate solutions aqueous. And I will, if you notice, the solution is lighter in color. That's because the copper ions are being used, and the copper ions are what we're giving it the blue color. Zinc sulfate, it's not colored, so it's clear. So that's why it looks like it's fading. And then you see kind of this dark stuff forming on the piece of zinc. That's the copper that's forming, okay? Because really, again, we get back down to our reaction. The sulfate's not doing anything. It's just kind of in there helping. But what's happening is the zinc is going from solid to aqueous. That's why the solution's getting paler in color. And the copper ions that we're giving the solution the blue color, they're now kind of forming that solid copper on that piece of metal, okay? So the zinc displaced the copper ions in solution. It reduced the copper ions because it's a stronger reducing agent, because zinc is higher up than copper on the activity series. So on this one, it's giving you the reactants, and it's asking you to predict if they will take place. And if they do, it's asking you to write that net ionic equation. The net ionic equation is this one here, where we get rid of the net anion. We get rid of the negative ion, okay? And we just have what's being oxidized and what's being reduced. So on all of these, you would need to check your activity series. So for example, I would see is K higher than PB? If it is, they're going to switch places, and then I can get rid of the nitrate and write just the net ionic equation, okay? If it's, if something's not above, like copper and zinc, if I check copper, copper's not above zinc. Copper is pretty close to the bottom. Here's copper, and then zinc is, where's zinc at? Zinc is up here. So zinc is here, copper is here. So copper cannot replace zinc because it can't reduce it. It's below, it's not a strong reducing agent. So like on number 4, I would just write no reaction, okay? So just like we have the activity series for metals, for the halogens in group 17, the stronger oxidizing agents are going to be towards the top. So fluorine's the strongest. The bottom are weaker oxidizing agents. So for example, if you have chlorine gas and you just bubble it through a solution that has bromide ions, chlorine will displace bromine because it's above it in its group 17. And so what you need to be aware on here is you need to be able to describe the changes. Because when you have chlorine gas is kind of this greenish, yellowish green gas, and the solution will be clear. What you'll see start to happen is bromine, when bromine, the element bromine is kind of that reddish brown color. So it'll look like it's changing from colorless to kind of a brownish red color. If you have something with iodine, iodine's always like a purple, like a purpley black color. So usually you have kind of yellow green to describe things that have elemental chlorine. You have kind of a brown or a red brown for bromine, and then a dark purple for iodine. So if you were to look at, like, for example, like number 1 here, okay, you're starting with chlorine, but you're making iodine. So you should see kind of a purple color form since you're making iodine.